So in this example, we're going to deal with two types of potential energy. Our gravitational potential as well as our elastic potential energy. So let's begin. Now a ball of mass 4 kilograms begins from a height of 60 centimeters, which is simply 0.6 meters, and falls onto a spring that is 20 centimeters long or 0.2 meters long. We want to find how far the spring compresses if the spring's constant is 1,600 newtons per meter. So let's look at our diagram. So our first position is right before the ball begins traveling. So at this position, at a height of 0.6 meters above the ground and at a height of 0.4 meters above our spring, our ball's velocity is 0 meters per second. So we let go and it begins traveling, and this position is the position right before our spring begins compressing, right before our ball hits our spring. Now this position 3 represents the position where our spring has compressed some unknown distance h, or x, and our velocity at this point is 0 because the spring completely stopped our ball. So our velocity is 0. So let's begin by first finding what the potential energy at point 1 of our ball due to gravity. So we simply use m times g times h. So our mass of the ball is 4 kilograms, our gravitational field is 9.81 meters per second, and our distance above our ground is 0.6 meters. So our joules of energy due to the gravitational potential of the ball is 23.54 joules. So now let's look at position 2. I want to find what my energy is, what my kinetic energy is at point 2. So remember, some of this gravitational potential was converted to kinetic energy because we're assuming no air resistance exists, and so we can assume that there is a conservation of mechanical energy. So some of this gravitational energy in position 1 went into kinetic energy in position 2. So basically what we're doing is we're calculating the amount of gravitational potential at position 2, at position 0.2 meters above our ground, and then we're subtracting that from the gravitational potential in position 1, and that will give us how much kinetic energy was transferred. So mgh equals 4 kilograms times 9.81 times 0.2 meters gives us 7.85 joules. And now we take this and subtract it from this, and we get the amount of kinetic energy at this position 2. So it's 23.54 minus 7.85 joules, and that gives us 15.69 joules. So if we want to find the velocity, we simply use this formula to find our velocity. But that's not what we want to find. We want to find what the distance this spring compresses. So we basically set up the following long equation, which basically tells us that our mechanical energy is conserved. So at position 2, we get the following equation. So our gravitational potential plus our kinetic energy plus our elastic potential energy is equal to everything in position 3. So our gravitational potential in position 3 plus our kinetic energy in position 3 plus our elastic potential in position 3. Notice that at the point where the ball, right before the ball hits the spring, our elastic potential is 0 because the ball is not really touching or compressing our spring. Our distance is 0, so our 1/2 kx or 1/2 kx squared is 0 because this h we're assuming is 0. Now, so this crosses out. Now let's go to this side. What is the kinetic energy when the ball hits and compresses our distance x? Well, the spring completely stops our ball from moving, so our velocity at position 3 is 0. That means we can cross out this part. So we get the following formula. mgh plus 1/2 mv squared, this corresponds to position 2, equals mgh plus 1/2 kx squared, which corresponds to position 3. Now notice this guy still exists because this distance, some unknown distance above the ground still exists, and so there is still some gravitational potential energy. Now, what is this h? Well, this h, this distance h, is simply this x minus this distance h, right? So, in other words, to find this distance h, we simply take our point 2 and subtract it from h, right? So, let's look at the following formula. So, we basically take this guy directly from this, and we get this guy directly from this. So this is our kinetic energy, which we found here, and this is our gravitational potential energy at point 2, which we found right here. And we add them up, and that equals mgh, so 4 times 9.81, h, which is simply 0.2 minus x, right? It's this distance. It's this distance minus this distance, which gives us this distance, plus 1/2 times 1600 times x squared, because k is 1600. So we basically add these guys up and we rearrange and we get the following equation. We basically bring everything to one side and we set it equal to 0. So 800x squared minus 39.24x minus 15.69, and now this is a quadratic equation. So we basically use the quadratic formula to solve for our roots. Quadratic formula states negative b plus minus square root of b squared minus 4ac, our discriminant, divided by 2a, where this 800 is our a, this negative 39.24 is our b, and this negative 15.69 is our c. So we plug in our values and we find two roots. One root is x equals 0.1667 meters, and the second root is negative 0.117 meters. So which one do we accept and which one do we reject? Well, let's go back to what we define our x to be. Here we said that our distance above the ground, once the spring is compressed, is 0.2 minus x. So our distance should be less than 0.2. If we choose the negative, we see that our distance is greater than 0.2, but that doesn't make any sense because we know our distance should be less because our ball compresses the spring to a smaller distance, smaller than 0.2. So that must mean our x must be positive so that our final distance is actually less. So our x is 0.1667 meters. So this is the amount our spring compresses when it travels a distance of 0.6 meters above the ground when the mass is 4 kilograms and when the spring constant is 1600 newtons per meter.